Now, when we are going to convert this equation into the dq domain, we have to be little careful about the mathematics. Okay. Here you see there is a L d dt of I g alpha beta. So, there is a differentiation of the space vector here in this equation. So, when we are covering when we are converting into the dq domain, we have to be a little bit careful about this differentiation. Okay. So, now recall, again I will ask you to recall from the lecture of alpha beta to dq transformation, where we had seen that a space vector, say any space vector, can be converted in one reference frame, can be converted in another reference frame by using this e to the power minus j theta multiplying factor or the conversion factor or operator, I should say. So, therefore, the if I want to express this current in the dq domain, then I will multiply by e to the power minus j theta. We have discussed this concept in the previous slide, in the previous lecture. Now, when we differentiate this ddt of I dq 0, then basically we are doing a ddt of e to the power minus j theta into I alpha beta 0. So, therefore, if I simplify, so left hand side remains like this. Now, right hand side we means ddt of y 1 into y 2, we differentiate by parts, and so ddt e to the power minus j theta into I alpha 0 plus ddt of I alpha 0 into e to the power minus j theta. Now, left hand side remains the same, and the right hand side is e to the power minus j theta. Differentiation of this is e to the power minus j theta into d theta dt, and that d theta dt is j omega here, okay, because we are assuming that the theta is rotating at a speed of omega. Okay. So, then this part comes, and then this part is as it is like here. Okay. So, we can say therefore, that this quantity here, this quantity is equal to ddt of I dq 0 plus j omega e to the power minus j theta I dq 0 t. Sorry, there is a mistake, this is I alpha beta 0 t. Okay. So, this is the equation here. So, we will use this equation 1 in the next step. Okay. So, now we said that this is the equation which we got from the alpha beta domain. Okay. We got this one, V conv alpha beta is R I g alpha beta plus L d dt of I g alpha beta plus V grid alpha beta, okay, in the space vector in the alpha beta domain. So, when we want to convert into dq domain, I will all multiply with e to the power minus j theta. So, I will multiply e to the power minus j theta here, 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 here like this, okay, all the quantities. Now, whatever I had obtained from this equation 1 here, whatever I had obtained in equation 1, now I will replace here in this equation. Okay. So, what I will get after substitution, you can do it yourself, substitute these values, and then you will find that such an equation comes up. Okay. Such an equation comes up, which on further simplification, okay, I am not doing this exact mathematics here, but on further simplification you will get V conv dq is R I g dq plus L d dt I g dq plus V grid dq plus j omega L I g dq. This is a part which comes new, okay, because the other parts were also very similar to the alpha beta, the other components. So, like you can see, compare this is similar to this, and R I g here, this is similar to this is similar to this, and this is similar to this here. Okay. but this fellow this term comes new in this equation, okay, and it is the term which we have to take care of. This is a problematic term, we will see that. So, this is what comes up in the equation. Okay. So, this is the equation. Now, we can again split. So, this is the space vector equation, this is in the dq frame of reference. So, splitting into real and imaginary parts. So, v con dq, what is v con dq is v con d plus j times v con q, converted d plus converted j times converted in the q. Similarly, I g d q is I g d plus j I g q, okay, and v grid d q is equal to v grid d plus j v grid q. Okay. So, then we can split this into real and imaginary quantities. So, the real part is this one and the imaginary part is the q quantity. So, the real part here is equal to I am collecting the real part. So, this we are splitting into real and imaginary quantities, and this whole thing again we are splitting into real and imaginary quantities. Okay. So, then we collect the real terms and then we see that this is the equation here and this is the imaginary quantity. So, one is the d axis quantity, another is the q axis quantity, right. There is of course, okay, we will see this one. So, I have rewritten this equation here. Now, this term here, so otherwise this equation looks very similar and familiar with the alpha beta circuit. D axis voltage and is controlling, you see all the d axis terms are there, okay. I g d d axis term and v grid d is the d axis term, v converted d is also a d axis term. However, there is one q axis term which is popping up here, okay, and this indicates that there is this I g q, I mean the q axis current has an impact on the d axis voltage. Okay. That is why it is called a cross coupling term, it is cross coupling. A d axis current is having an impact on the q axis voltage and the q axis current has an impact on the d axis voltage. So, here also second equation you see there is a d axis current and then this is a q axis voltage and this is a d axis current. Okay. Okay. So, this term, this cross coupling term is something which is not desirable. Okay. We do not want to have this cross coupling term. Why? Because we want to control, when we want to control d axis, say we want to control the d axis voltage, we do not want an interference from the q axis current, because we will want to control the d axis current. So, we will change the d axis voltage, okay, and so that the d axis directly flows, which again indicates that I can accurately control the power, active power P. So, active power is, later we will see, active power is getting controlled by the d axis current and reactive power is controlled by the q axis current. But when we want to control the P active power, we do not want to change the q. So, we do not want an interference from the q axis current. Okay. However, this equation tells us that if we do such a thing, if we change the d axis current, there is an impact on the other axis voltage. So, this factor needs to be nullified. Okay. This is inherent in the model of the VSC. Okay. The VSC itself behaves like that. Okay. The inherently VSC has this cross coupling factor inside the what I should say, inside the model or inside the dynamics of the converter. So, this thing, this effect must be compensated in the controller. Okay. So, the controller, we will do some tweaking in the controller by adding a feed forward term. Okay. We will do some tweaking in the controller by which we will try to nullify or minimize this cross coupling effect. Okay. How we will do that, we will see, but the essentially the idea is that the VSC has this cross coupling thing inside it, and we will then try to nullify with the help of the controller, where inside the controller we will add a feed forward term. Okay. So, as to compensate this effect, and then what happens is that it becomes very nice control system. Okay. D axis voltage controls the D axis current, and more importantly we will see at the last stage that this will become a nice second order system. Okay. For this L filter case, it will become a very nice second order system where we can control very nicely, we know how the behavior is. So, anyway, so we will come to that now. So, therefore, now we can draw the equivalent circuit. So, here I am showing you the equivalent DQ circuit. So, from this circuit is obtained right from the equation we have derived in the last slide. Okay. So, you have the V conf and D axis voltage and D axis current and V grid D, but there is this cross coupling term coming up. Okay. So, here important thing is all quantities are DC, these are all DC quantities. Okay. I grid, IGD, IGQ, they are all DC quantities, but we may have perturbation in that, we may have transient we have transient change, but at steady state all become DC quantities. So, so far we have seen how the model of the VSC appears, and this is the two circuits of the VSC, D axis circuit, Q axis circuit, which we will further deal with, but in order to deal it we will go into the small signal model of the circuit. Okay. But I will just for the time being I will just pause at this point and we will go into something else. Okay. Before I go into this okay. So, how do the space vectors look like from the DQ reference frame? Now, we will see the space vectors in the DQ reference frame. So, here we see that there is a D axis and there is a Q axis, and these two axes are rotating and all the space vectors are all also rotating. Okay. This is we have discussed it as part of the Parkes transformation. So, we see that if the D axis is rotating at the same speed as the grid space vector or the converter space vector or the grid current space vector, then all these quantities will now look as if they are stationary with respect to, means if all of them have the same velocity, then they will appear to be stationary, and that is why they are appearing as DC quantities. So, this is the D axis and Q axis, how these space vectors look like. Now, how what is the vector control of grid connected VSC? Now, in vector control strategy of the grid connected VSC, what we do is the rotating D axis in that DQ reference frame is aligned to the grid voltage space vector. That means, this D axis is now aligned with the grid space voltage space vector. So, we first find out where is the position and what is the speed of the grid voltage space vector, and the DQ transformation, in the DQ transformation the theta is aligned with the grid voltage space vector. So, then they both of them gets aligned with each other. Okay. So, we have some advantages if we do that, we will see that. So, this is called the grid voltage oriented vector control strategy, and this is nothing new. I mean, it all comes from the machine control, okay, from say for example, induction machine control, but we have all derived this, that is why the word vector control is still used here. Okay. So, we are aligning the grid voltage space vector with the or we are aligning the D axis with the grid voltage space vector. So, once we do that, what do we see? So, earlier this D axis and V grid were separate, now they have become aligned with each other. Okay. And of course, q axis is 90 degrees leading, and they are all rotating. Okay. They are all rotating with each other. So, once we do this, okay, what is the benefit? What do we get? So, once I have aligned the d axis with the grid voltage space vector, then I can always say that the V grid q becomes 0. Okay. The q axis component of the grid voltage space vector becomes 0. There is no q axis component, and the V grid d is the entire space vector magnitude. Okay. Here it is perfectly aligned. So, therefore, once this happens, then I can modify the equation 2. Okay. So, we will make in that equation 2, we will make V grid q to be 0. Okay. And then we can write these two equations once more. We will come to this equation sometime later when we are doing the small signal modeling, but this is once we have aligned the d axis to the grid voltage space vector, then we get to these two equations. Okay. Now, let us for a moment look into the power situation, power scenario. What is the equation there? Okay. Because we have so far done with all the voltage and currents and etcetera. Now, let us see what happens with the power in the dq domain. So, the power in the dq domain is given as Vd Id plus Vq Iq. Okay. Again, you have to refer to the previous lecture. Again, there is a term 3 by 2 here. Now, we have said we have made Vq equal to 0. Okay. So, therefore, now we can directly write that the power which is exchanged by the VSC with the grid is such a factor. Okay. Now, important thing here we say that P grid T. So, this was instantaneous power, and so we can say that the power here is 3 by 2 P grid D into IGT. What is important here? The important thing that we note here is that this power, okay, suppose the grid voltage is perfectly known and it has a fixed value. Okay. So, if V grid is fixed value, then the P grid, I mean the power which is exchanged by the VSC with the grid, that power, once this is a constant. So, this is a constant suppose, then the P grid is entirely controlled by IGD, okay, which means the d axis component of the grid current entirely controls the power exchange, okay, and there is no influence of the q axis. Okay. So, this is what was important, because this is the vector control strategy. Okay. Let me do the q grid. So, you can also see qt, and we can write this equation here, and again we have made that V grid q equal to 0, and so we put like this, and we see that the q grid is entirely controlled by the IGQ. Okay. So, we see that IGT is responsible for active power and IGQ is responsible for reactive power flow with the grid. So, if we change the IGD, we will change the P grid, and if we change IGQ, that is the q axis component of the grid current, we will change q grid. Okay. So, this is a decoupled control, they do not affect each other, okay, and that is why this vector control strategy is the vector control strategy, this term comes. Okay. So, like in machine, like we say that we will control the torque and the flux independently. So, with one current we will, the d axis current, we will control the flux, and with the q axis current we will control the torque of the machine. Okay. and they will be done independent of each other. Once we have fixed the ISD or the d axis current, then you can control the torque seamlessly with the help of the q axis current. Similarly, here if you fix the value of IGD, you can seamlessly control the value of q grid with the help of IGQ. Okay. So, this is the benefit of this type of a control. Okay. So, again also this also has another thing that you should note is that the voltage source converter, it is a voltage source, however, it is a current controlled voltage source. Okay. You see you are controlling the power by controlling the current. Okay. So, it is a current controlled voltage source converter. So, a vector control essentially is a current controlled strategy, you are controlling the current. So, if you see that in vector control, it gives a lot of I will say a lot of implication. Okay. So, this is beyond this scope. So, I will not go into those details, but this is a current controlled. So, the whole VSC now behaves as a current controlled converter. Okay. Voltage source current controlled converter. Okay. So, now we are now slowly moving into the control system, okay, converter and the overall control and the overall converter structure. Okay. So, you see here there are lot of blocks, okay, a lot of blocks here, and so we should first identify each block one by one. So, we have seen some of these blocks earlier. So, first of all this is your VSC, okay, this VSC and this is x power and here is your grid. Okay. This block we have said earlier, this is the PLL, and we also get the theta from there, and we do the we sense the current, okay, through a current sensor, and we can convert that current into alpha beta and to dq, so as to get the feedback of the grid d axis current and grid q axis current. So, this is the feedback. Okay. So, we can always get this, these two are the feedback items. So, we know what is the feedback current. Now, again I told you what do we want for the VSC, we want a PG star and a QG star. So, the PG star has to be replicated to the grid, how much is the d axis current. So, we from the PG star we get the from this, suppose this is 100 watt or say 1000 watt and maybe this is 500 var. So, we have to convert this watt and var into a current reference ampere. Okay. And how do we do that? We have seen that under vector control the power and the d axis current are proportional to each other with this value constant. Okay. So, if we multiply with this, then we get the IGD star and IGQ star. So, this will become the reference for the control system. So, if there is a reference and there is a feedback, then we will pass it through a regulator, okay, PI regulator. Of course, there may be other types of controllers, but we have seen that PI regulators work quite nicely. Okay. Let me see if okay, yeah. So, this is the overall thing. So, I have split into a few slides. Okay. Yeah. So, we see that we get IGD star and we get also IGQ star. Okay. So, this is converted reference d axis assuming grid voltage to be controlled. Now, we have two variables because we want P and Q to be independently controlled, and then we have the PI regulator. So, you can have a different types of control, different variety of controls are possible, but we have seen that PI controller gives sufficiently good performance in many of these applications, and the steady state error is also 0, and we will have like 2 controllers will be needed. Okay. So, we will have like only the d axis control and the q axis control. So, this pi controller is nothing but this form of a this is inside this block here, okay, like this. Okay. Okay. Now, after this block, okay, after this the output of the controller is, there are two terms here. You have seen this term, okay, before. This term is something as a, this is the feed forward term in the controller. And you see what is this feed forward? As I told you before, in the model of the VSC, there is this cross coupling term, and this feed forward term here we are deliberately adding inside the controller. Why are we adding that? Because we want to nullify the effect of that cross coupling term inside the VSC model by this term inside the controller. Okay. So, you see these terms here and here, these two terms are exactly similar to what we have seen in the VSC model, and so we will add this here right itself, and we will see that how they, means they can be, because of the control action, their effect can be completely nullified. Okay. The cross coupling terms effect in the VSC can be completely nullified by this feed forward term. In case of machine control, you will see that there will be an additional term. Here you are seeing there is two single terms. In case of machine control, you will see two additional terms coming, or I think that was like the back EMF thing. So, yeah, so there will be an additional feed forward, and so what I want to say is this structure is very similar to a machine control structure. Maybe you will have one or two terms extra there as part of the feed forward, okay, because there is some another term comes there. Anyway, we will not go into that details. So, here is the dq to alpha beta and then alpha beta to ABC transformation, because once you have got this Vd star and Vq star, so you then have to, because these are DC quantities and they are in the dq frame of reference. So, then we want to get it back to ABC frame, and so we use the inverse Parkes transformation, inverse Clark's transformation, so that ultimately we get this Va star, Vb star and Vc star. These are the reference to the modulator. We have extensively discussed the modulator before. Okay. So, we said that the sine wave is compared with the triangle. Where do the sine wave come from? This is the where the sine wave comes from, Va star, Vb star, Vc star. These are the sine waves that come. So, you can have sine PWM or space vector PWM, and then you can do it here the SA, SB, SC, these are the gate pulses to the VSC. Okay. So, this is how the whole system works here. Okay. So, you should understand the whole structure of the voltage source converter and see what are the components here. Now, in order to do this control system or in order to see the controller structure and everything, we have to go into the small signal model of the VSC. Okay. So, those equations which I said that we will come back to this equation, those equations have to be now transferred into small signal equations. Okay. So, what is small signal? Small signaling means that you have a DC quantity like this, you give a small perturbation and see how it is a small perturbation, and so you see how the small variations, how that transfer function looks like in presence of those small variations. You can see any book on control system and can just refresh. Okay. So, the equations that we had in the D and Q domain. So, now we will write it once more here, and what we will do is we will linearize this system around that particular operating point, giving a small perturbation. to the input variable. So, we will give a small perturbation to each of these variables, and so which will be kind of like a small AC quantity over the DC quantity, and then we will linearize and we will see how the performance looks like. Okay. So, from there we will derive the transfer functions and will apply the linear control system theory. So, what we will do? So, we have this V conv d, and so what we will do, there is a steady DC operating point and there is a small hat quantity. Hat quantity means a small perturbation, V con d hat, okay, where V con d hat is much less than V con d, small perturbation. So, you can do this for all the variables. Okay. So, you can do it for this, you can, so V conf q, we can do for IGD, IGQ, you see these are all small variations. Okay. We can do, but again this variation is small. Now, we put it back into the previous equation. So, then I can write V con d plus V con d hat and then R I G D and L. So, all these we put it, and then we collect these hat terms or the small AC disturbance terms. The AC terms are all collected, and so we get such an equation here. Okay. So, this is the small signal equation of the VSC in d axis reference frame. So, this was the d axis one. In a similar way, you can also collect the AC terms from the q axis equation, and we get this equation here, and this is the small signal equation of the VSC in the q axis reference frame. So, in order to get the transfer function, we will apply the Laplace transform to these equations. These were all time domains, now we go into the S domain. So, therefore, V con d is this one, and V con therefore, V con S, okay, V con d S is R I G D S plus L S plus minus omega L I G Q plus V grid d. Okay. So, we can say that we can collect all these terms and simplify. We say that V con d S plus omega L I G Q S minus V grid S is R plus L S times I G D S. So, we have now collected the voltage terms on the left hand side, the current term on the right hand side, and there is this R plus L S term coming, and then there is this cross coupling of the VSC. Okay. This is inherent, as I told you, this is inherent of the VSC. So, this is how it looks like. So, similarly, you can do with the V conf q, converter q in the S domain, and can write something like this, and of course, I have assumed V grid q to be 0. So, the IGQ is also like this R plus L S, but then there is the cross coupling term in the VSC model, right. So, now I can graphically draw this as part of like blocks. Okay. So, you see here V conf d here is this one, then V grid d. So, I am just following this equation. So, the output is the IGD. So, this is the output of this block here, and we are giving a voltage V con d, and the output is the IGD hat, this is the current, and then this IGD had this with this omega L, it comes here. What is important is that there is a V grid d effect of this V grid d S here, but what is important is that this is the R plus L S term here. Okay. So, if somehow we can get rid of these two terms by somehow, that is what we had just previously mentioned, that this feed forward term inside the controller, okay, the feed forward term inside the controller will help us to nullify this effect of these cross coupling terms. Okay. If we can do that, then this grid connected VSC is acting like a simple RL circuit here, because this is the transfer function of an RL circuit. Okay. So, you give certain voltage here and you get certain current with a first order lag, it is like a first order system. Okay. So, the whole VSC, if we can neglect this one, if we can nullify the effect of these two, then the whole VSC becomes a kind of like a first order system. Okay. And of course, we know that this cross coupling term is not a desirable, which means that it will degrade the controller performance. And so, then we add this feed forward and we assume that this feed forward, because of this controller action, because of the closed loop system, will be able to fully nullify the effect of this cross coupling term. And so, then so we can write this as a block diagram here. Okay. This is the small signal DQ model of the VSC, inside which has its inside this whole blocks here. This is the small signal DQ model of the VSC. Now you see that this is the VSC model. So, now we are in the control structure inside the control blocks. So, this is the small signal DQ model of the VSC, which is nothing but this equation here, okay, working. And inside the controller we have this feed forward term. So, this is the feed forward term. So, this is kind of like the plant, this is the feed forward term, and this is the reference, this is the regulator, and this is the output. Okay. So, you see how the control structure looks like, the whole control structure, and this is very similar to what we already know, and this is very much familiar to us. The good thing about this plant is that it is a first order system. Okay. And because with the feed forward term we have already cancelled, we have ensured that the cancellation happens of this cross coupling term. So, the plant becomes a first order system. Okay. And that is a great benefit, because now we know we have full command of the control system, because we have a PI control and a first order system. So, the whole loop, once we close the loop, the closed loop system becomes a second order system, and we can control the transients, we can control the overshoot, we can control the settling time, etc. Okay. So, this is how it works. So, therefore, that is what I have written here. The effect of the cross coupling term should be nullified by the controller, but again of course, yes, this is a point, and accurate knowledge of L is needed for adding this feed forward term, because in the L, in this feed forward term you have the L. If the L value is changing, then you have a problem. Okay. So, then you have some challenges. Okay. So, anyway, so once this is done, then you have this thing, and then once the perfect cancellation of this cross coupling term happens with the feed forward term, then you get something like this. Okay. You see, this is a nice second order system. Okay. You have a Kp plus Ki by S, and you have a 1 by R plus Ls in this. We have, so there is one D axis controller, and there is one Q axis controller here. Okay. It is a very nice second order system, and we have full control over what we can do with it. We know exactly how this behaves. Okay. So, so now we have that, we can write down the transfer function of this system. And so, what is IGD, the actual current divided by the IGD reference, IGD star. The transfer function is SKP plus Ki. So, you just multiply G by 1 plus GH and you get this. Okay. Similarly, IGQ is something like this. Okay. Very much familiar to what we already know. Okay. then it is possible for us to tune the regulator parameters, the values of Kp and Ki. Of course, it is a big chapter on its own. Okay. You can there are a lot of techniques, but one of the techniques that we frequently use is the bode plots. Okay. And with the help of the bode plots, you can place or you can change the loop gain characteristics of the control system or the controller. I will not go into that details, because that itself is a big chapter on its own, but I will recommend or I will suggest you to look into the book by Robert Ericsson and Maximovich, Dragan Maximovich, Fundamentals of Power Electronics. That is a very nice book, and that book has a whole maybe 1 or 2 chapters devoted to how you can easily, with the help of bode plots, you can easily change the characteristics or the closed loop system character, the loop gain of the whole system. So, it is a very nice book. So, but I will not go into that details, but I will just say that okay, with this thing, okay, means just to give you small introduction, characteristics equation here will become similar to s squared plus 2 zeta omega n s plus omega n squared, and it looks like this. And so, we can set the values of Kp and Ki. For example, Ki is this and Kp is, you can put these values. So, suppose take an example, filter is there with chosen with L equal to 0.1 millihenry, R equal to 0.1 ohm, and then we can choose that the bandwidth is 2 pi into 200 radian per second. That is fine enough, good. 200, if the variation in the variables are in the range of say 10-20 hertz, then yeah, this will be okay, 200 radian per second, and you can take a value of damping factor as 1, and so this Ki and Kp can be chosen like this. Okay. So, again this is a very just a small introduction, but it is just to give you a flavor of what is what we do in this case, how we design the controller. Okay. So, therefore, what we have, so let me summarize a little bit what we have covered here. So, first we saw the VSC modeling, and then we say that okay, these are all 3 phase quantities, we have to transfer it into 2 phase. We can control with 2 phase, but there are some issues with if you go into the powered active reactive power like hysteresis control and then the variable switching frequency. So, we can go one step ahead and go into a DC domain with the help of the Clark and Parkes transformation, and with that DC we can apply our linear control system theory. We give a small AC perturbation to these DC quantities, get a small signal model, apply the transformation and get it back into the AC 3 phase AC quantities, by which we can control the VSC. When we model the VSC, what we found is that there everything is fine. I mean, there is a D axis, there is a D axis circuit and there is a Q axis circuit, but they have a cross coupling between them. So, the cross coupling term degrades the performance of the VSC. So, what we do in the controller, we apply a feed forward term, so as to cancel the effect of this cross coupling term. And once this perfect cancellation happens, then you can see here that the whole VSC, the grid connected VSC with a L filter behaves like this system here. Okay. And this is a second order system, a nice second order system by which we can control the grid IGD star and IGQ star. Okay. With a yeah. So, of course, IGD star is basically controlling P star, IGQ star is controlling the reactive power. Okay. One is controlling active power, one is controlling reactive power, and they are independently being controlled. Okay. Of course, you can extend this analysis to other types of systems, like what happens in LCL filter. Okay. If you have not L filter, if an LCL filter, equations become a little bit more elaborate, but the control but the philosophy remains essentially the same. Okay. So, here therefore, we conclude and yeah, we conclude. We will take a few examples in one of the next slide, one of the next lectures about some of the simulation results of grid connected VSC as well as for 2 level converter as well as multi level converters. We will take up in one of the next lectures.